All right, as a summary of the previous video and then the video that we talked about, a few videos back, there's a few definitions that I want to talk about. So it turns out that if f has a Taylor series expansion on some disk, let's say some disk, I'm just going to call it D, but some disk centered at z0 of radius r, then we say f is analytic on D. So analytic means that f has a Taylor series expansion, meaning that you can write f as a power series, and the power series has the usual formula. So if f has a Taylor series expansion, we call it analytic. What we have just shown in the previous videos is that every analytic function is holomorphic. Okay, so if it has a Taylor series expansion, it's holomorphic. If it's holomorphic, then it has a Taylor series expansion. And so we can summarize the two previous videos, or two of the previous videos, in kind of the mantra that holomorphic is analytic. Okay, so that's kind of our motto, I should say. So holomorphic and analytic mean the same thing. So it turns out that if a function is analytic over some region, then it's holomorphic there. And if it's holomorphic over some region, it's analytic there. Analytic, again, meaning that there's a Taylor series. So if you remember back in chapter 1, we talked about how there's two words for holomorphic. The other one was analytic. This is why. This is why it's okay to call holomorphic functions analytic. It turns out that once you have one property, you have the other. Okay, so it turns out that they're equivalent properties. Okay, so that's what we just did in the last video or two, show that all holomorphic functions are analytic and vice versa.